And then
I thought it said.
Hi, we record. So she's an outstanding grad student. She has been working with the band collaboration, which is the same collaboration that I am part of and that I came with to work. Most of her work on her PhD has been thinking how to approach the problem of mixing and combining models in a Bayesian way for several different topics in nuclear physics. Not only she's amazing on the work that she does in terms of academic endeavors, but she has helped organize some career sessions that we had in the collaboration, and it has been a pleasure to work with her. She was also part of the organizers of the previous Theory Alliance summer school. So just incredible. You're going to see an amazing presentation today, and I invite you to welcome her for her talk. Thank you, Alexandra.
All right, thank you, Pablo. I'll try to live up to that. All right, so as Pablo mentioned, this is band collaboration work, also with the BUQEYE collaboration. For those who do not know, Bayesian uncertainty quantification errors in your EFT. So these two collaborations with Christian Drischler, Dick Bernstall, Jordan Melendez, and Daniel Phillips are also on this work. So this is an interesting look at Bayesian model mixing, which I'll be explaining, and if you're unfamiliar, and applying this to dense matter. All right. So just quick outline. Going to go through what dense matter is, why we care about it, some information about the low density side, as you'll see that we're using, which is Chiral EFT, and then some going over some of the uncertainty quantification for that as well, because we're Bayesian and we care about truncation error. High densities, we are looking at perturbative QCD, so we'll talk about that. And interesting approach that we took to convert between different variables for our model mixing. And then I'll go through some of the results for model mixing and talk about some extensions that we plan on doing. Okay. So when you think about dense matter, you think about the equation of state, a lot of times you think about neutron stars. So that's what we're going to start with. This talk, as you can see at the beginning of the slide, is on symmetric nuclear matter. So not quite neutron stars, but I like to begin here because this is something that people are very, very familiar with. So neutron stars, as we know, are some of the densest objects in the universe, which makes them very interesting because there's a lot of very unknown physics, some known physics, a lot of unknown physics still going into these. So as you can see on the side, I just show this kind of cross section of what they look like. So we have a good understanding of what's going on maybe at the top here with the outer and inner crusts and the outer core, where you look at nuclei, so neutrons and protons, electrons and muons. And then as you go down farther, there is some kind of phase transition, most likely going on here, where you go to possibly deconfined quark matter, possibly kaons or pion condensates, or anything like this that's been proposed. Still relatively unknown here, so that makes this very interesting to look at. But there's also the possibility as well of not just looking at neutron stars, right? Because these are not the only things that we care about, but the entire phase diagram. So neutron stars live around here on the phase diagram, which is up to about maybe 6 to 10 times what we call saturation density. So the typical central density of a heavy nucleus like lead, something like this. But of course, the equation of state can describe, or should describe, all of the physics that we care about here. So we're also looking at quark gluon plasma way up here with deconfined quark matter. We're looking at, and this is also in temperature, right? So we're not just looking at 0 temperature, we might be looking at very, very high temperatures as well. And then a lot of different physics going on, some phase transitions that we're trying to understand. But for this talk, we are doing kind of the, I would call infancy work on trying to figure out how to combine different models that people have developed for the phase diagram. But in our case, we're only going to be looking at 0 temperature. So this is where we're living. Okay, so going into that regime that I just mentioned, what we want to do is, we know that there are different QCD-based theories. There are many other theories as well that are not entirely QCD based phenomenological ones. But what we wanted to do is look at the QCD based theories that we have and see how we can connect them or understand and learn from what we already know in regions where we have very, very well constrained models with uncertainties that have been fully quantified. So as you can see in this diagram, this is the pressure scaled by the free pressure and the density scaled by the saturation density on the x-axis. And we all know very well now, because of BUQEYE collaboration and other people before them, how chiral EFT works and very well at low densities. So this describes, like I was just kind of pointing out here, this is where neutron stars in this kind of density range is, and chiral EFT can cover up to about twice nuclear saturation density. So this is very well understood. These are, I think, some of the most constrained understanding on the symmetry energy comes from chiral EFT constraints most recently. And then there's this large region in the center where we really don't know a whole lot yet, and we don't have much data to constrain this region. And then we go all the way up to densities like 40 times saturation or so, where there's been a lot of really good work done on perturbative QCD on this side, where we are at the point where we are at a high enough density that you can take a perturbation or perturbative expansion of QCD in quarks and gluons and look at what happens there, which is not something that you can do down here, hence the effective field theory. So this has been very, very well described as well. And there's a lot of ongoing work too, to look at higher and higher orders. But then in the center, as I mentioned, what are we supposed to do here, where there's a lot of region, a very, very large region in density, where we don't know a whole lot. So the question that we have is how to connect these, not only how to cross this region and figure out what is going on there, or maybe get some kind of inference from chiral EFT and pQCD and whatever else we can use, but also to get an estimate for the equation of state that has well quantified uncertainties. So as my friend Jordan Melendez would say, hopefully you can Bayes your way to victory. Okay, so I'm going to talk a little bit about the theories themselves before jumping into what we're actually doing with them. So at low densities, as I was mentioning, you have the equation of state from chiral EFT. So I know a lot of times whenever I see talks that use chiral EFT, there's not a lot of explanation for it. So I'm going to kind of go through it a little bit for those of you in the audience who may not be as familiar with it. So as I was mentioning before, QCD at very, very low energies is non-perturbative. So I can't just take a perturbative expansion and calculate it in terms of quarks and gluons when my degrees of freedom at that level are nucleons and pions, as we know. So what we're going to do is build some kind of effective description of this that also hopefully includes all of the symmetries that I would expect from QCD. So this is as usually said, the most basic Lagrangian that you can write down with all the symmetries of QCD is this effective Lagrangian. But of course, that still means that I have an infinite number of diagrams that I can calculate, because even though I have only used the symmetries that I know of, this is still quite a lot of physics to quantify. So what I do, or what one does, since all of this work was done by Christian and his collaborators back in 2019, what you do is you use something like Weinberg power counting, and you can organize all of your diagrams into orders of decreasing importance that is based on some effective or some scale separation. So in chiral EFT, that is the maximum either between the momentum or the pion mass, and this is over a breakdown scale, which on most recent calculations has come out to be around, I think, 600 MeV. So if I can establish the separation of scales between very, very low and high momentum scales, then I can organize all of the diagrams that I'll get from my Lagrangian into this power counting scheme. So that's how I can organize this. Then when I go to these different orders, I can look at how to calculate single particle energies from this, because I need to take this Lagrangian into some observable that I can actually look at. So I can use something like many body perturbation theory or any other ab initio method to calculate this and propagate it and get energy per particle from these from this chiral Hamiltonian. So then that's what's done in the field previously. And we are not reinventing the wheel or anything here. I'm just showing this for some background. We use these results that we're coming from this paper in our calculations. So also what we do here is look at the work that was done using the N potentials from Entom, Machlight, and Nozick with 3 N forces included. And then in this scheme, these low energy constants, which are indicated by the numbers here, are going to be fit to experimental data. And I believe these were fit to the triton binding energy. And also employ a momentum cutoff because we'll need one of those. So this is 500 MeV for us. Okay, so that's the chiral EFT. How I would get these mean curves, as I would call it, from chiral EFT. But then there's the question of, if I'm only able to calculate or only want to calculate up to, say, something like N3LO, then I know that I'm going to have truncation error coming in from N4LO and all the orders that I haven't included. So how do I include information that I know I'm missing? So this was work that was done by Jordan Melendez and Daniel and Dick and collaborators back in 2019, which I think many people in the room are familiar with, to do uncertainty quantification on effective field theories. So what they do is they wrote a package called GSUM, which you can go look at if you want to later, that lets me quantify this truncation error by writing my observables, which are these y of x or yk of x here, as some reference scale multiplied by a geometric sum or a geometric series of the some coefficient c sub n of x and some expansion parameter q. So this example here is not a real EFT, this is just a toy model, but I like this because it shows that these are the predictions that I would get at different orders. And then if I look at this far side and I figure out what q and y ref are, I can plot the coefficients on this side. And if I can do this with my known orders, then I can use information from the known orders to get information about the orders that I'm missing. Because if I have put all of my physics information and my dimensions into my reference scale and into my expansion parameter, which, as I was showing for chiral EFT, was this max p m pi over lambda b, then if I take all of this away, then I can look at these curves, these c sub n of x's, and they'll be naturally sized as long as I have a good convergent EFT. Then I will end up with something where I can look at these curves and they're pretty much of order 1 or so in their variations. So what this means is that I can hopefully use something like a Gaussian process to emulate what these are for higher orders as well. Because I already know all of the physics information that I need from these orders, or at least how this convergence will work. So I can figure out what these coefficients should look like. So then what this package does is it incorporates all these correlations in Y as well. So this makes it very, very nice to include as much information as we have available to us. And we can also constrain some parameters of the Gaussian process that we use to estimate these coefficients. So you can put different priors of representing the information that you know. And then you will be able to test what you get from these coefficients as well with diagnostics like the Mahalanobis distance and pivotal Cholesky, which I'm not going to get into. You can ask me afterwards if you want to know more about those. But this is at least a good way to see if what I'm doing is actually quantifying my uncertainty and I can trust the statistics that I'm getting. Okay, so this is what I care about, is these coefficients here. And then really quickly, before I get too far into what we're using or how we're using this, I wanted to talk a little bit about GPs just for kind of a crash course in case you were not familiar with them so much. So I think in the language of MLR, this is a model extrusive emulator. So it's not doing anything, it's not changing the model itself, but it is using information that you're feeding into them to quantify what correlation structure you're seeing. So what the literature usually says is that these are random variables, any subset of which possesses a Gaussian distribution, which is a little bit abstract to me. So I like to just say that these are emulators that are defined by a mean function and a covariance function. So in practice, I care about this because the mean function will look at the trend of my data, and the covariance function will parameterize this correlation structure between points. So you can kind of see this in this figure that I have plotted here L, so this is the length scale. So this is one of these hyperparameters that you get in your Gaussian process that comes in through kappa. And then also the C bar will also be another hyperparameter. So these are what are trained, and then this is what creates this Gaussian process essentially. And then once I've trained these parameters, I can predict at points that I don't already have, and then this will help to map this correlation structure forward. So what it's doing is looking at how long the remembrance essentially of the data is. So how long does this is this structure remembered by this data? And then the C bar is looking at the variations around the mean. So this is a really nice way to include correlation information, as I will show when I actually start getting into how we use this for our model mixing. So then going back to chiral EFT, so as I said before, we have these mean curves. And so just pretend that there are no error bands here, and we just have these mean curves. Then how do we get the error bands? So we can use on energy per particle, this GSUM package. And what you can do is, in this case, we trained in the Fermi momentum because that was more stable than the density, but then you can convert this back to density as is done here. So what you do is you pick this expansion parameter Q, which is this, in this case, the Fermi momentum over the breakdown scale. And then the YREF that was chosen for this is what best captures the information at the leading order. So that's why this is in this KF squared format here. And then once I've picked these two, I can again do exactly what I mentioned before and plot the coefficients at each known order that we have. So we're going up to N3LO here, that's the red ones. So I can see that these are pretty naturally sized. So that indicates that I've chosen a good expansion parameter and a good YREF so that most of the information here can be captured by this Gaussian process framework. So then once this is fitted, I can predict for these unknown orders. And then these truncation error bands at each order are showing how much is the truncation error that I'm still missing. So as you can see, they're pretty close to being within each other's bands, which is a good, also a good indication that this is converging well. So then this is for energy per particle. So then what I use, because we're looking at pressure, is the pressure. So in the framework for this, we're able to propagate these uncertainties from E over A to the pressure. And you can see this is just a simple derivative in density. So then when I do this, I can look at these truncation errors, and of course they propagate well, and everything still looks really good. Okay. Okay, so now I'm going to talk about the high density side. So skipping all the way over to about 20 to 40 times saturation now. So very, very far away from where we just were. Now we are in the regime of high energies where QCD is perturbative. So I can take a perturbative expansion in the strong coupling. So this alpha S here that is shown up here. And I can write this in some order by order expansion of this coupling constant. And now I'm working completely in quarks and gluons as well. So that's something to keep in mind. And we're also working, in this case, there are many different ways you can do this. We chose to work in the massless regime. So massless UND quarks with equal chemical potential. And this is, again, in symmetric nuclear matter. So there's only two types of quarks here. So then this side. So also, for some more information, if you're unfamiliar with the way that perturbative QCD works and the strong coupling constant, this is something that you can expand. You can look at the particle data group or something like this. And you can also see that it's logarithmic. So that'll be important later on when we look at how these are converging. But in our case, we use this two-loop running for everything that we're looking at to recover lambda QCD. at the values that are experimentally determined. So what we do is we were using information because we can't, again, we're not going to reinvent the wheel, and all of the amazing work that's been done by Kirkella and Gorda and all of their collaborators over the past, I think, like 10 years, where they've been looking at doing hard thermal loop resummations to get these non-perturbative or these screening effects that you start getting the more and more orders that you add in perturbative QCD. So they've been doing a lot of work on this, and they're up to, I think, the very final term in N3LO, where they have not quite solved that yet, but there are many terms in this expansion at that order, and they've gotten all of them up to that point. So we decided to take their N2LO result because that one was the one that was fully done. And they have produced the curves, and they have, they're working on some very interesting missing higher orders estimation. But what we wanted to do was see how this BUQEYE truncation error framework held up when we used it on pQCD. So that is the main question, is how do we get these truncation error bands for each order? But also, if you're paying close attention, you'll notice that all of this is performed in terms of the chemical potential, which I can't just mix with the density. I have to be in both the same input space for both. So I need to figure out a way to get from the chemical potential to the number density, which sounds very, very easy. And as we were doing this, we realized that maybe that's not actually true, and there's a lot more behind this than we originally realized. So a bulk of the time that was spent on this project actually was figuring out the inner workings of pQCD and how to go from chemical potential to number density. So these are the two questions that we have from this side. So I'm going to talk first about the last one I mentioned. So how do you convert from chemical potential to number density? So we realized while we were trying to figure this out that if you just kind of blindly try to convert between the two, you realize that you are not actually matching up correctly in thermodynamic consistency. Thermodynamic consistency meaning that there are higher order terms that can come in if you're not careful. If you look at the different derivatives that you're doing, if you don't truncate consistently, then you're going to be mixing these orders. So what we did was we used this, which has been done before, but not, I think, in pQCD. You can find this in like Feder and Velechka's many particle systems book. So the goal is to transform this from PV to P of N. Also, this is the only mathy slide, so please bear with that. So the first thing that we did was we did a perturbative expansion in the chemical potential up to second order, because we only have N2LO results, so we can only go that far consistently and trust what we're getting. And then what you do is you Taylor expand the number density, which is just this derivative of the pressure with respect to the chemical potential. And then you figure out what your Fermi gas term is. And then the way this works, I think it kind of escapes me where we see this now, but I know that we see this in different cases, and I'm sure many of you have seen this in your research, where we're trying to basically reorder this. So once you pick this first term, every other term that you're adding has to equate to 0. So what we're doing is pulling a term and then solving for mu1 and mu2 such that this entire expansion is preserved. So when you do that, you basically kind of have to power count in terms of alpha S. So what we did was we looked at how to figure out what mu1 and mu2 are in this perturbative expansion by power counting the number of terms of alpha S involved, since that has a specific number of, or a specific power of chemical potential attached to each one. And I'm not showing mu2 because it's like 6 different terms, so you have to take my word for this. But then once you do this, you're able to expand P of mu again, but only keeping up to second order again, so it's all consistent. And reinsert all of these terms, do something like 10 pages of algebra, and then you end up with this at the very, very bottom. So if there are a couple things here, one, we're scaling this by the Fermi gas pressure, because when we do our model mixing, it's much easier to mix things that are on the same scale. So if you look at Chiral and pQCD, they're at very, very, very different levels in MeV. So MeV for Fermi cubed. So we scale this by the Fermi gas pressure. Second thing is, if you look carefully, everything is now dependent on N, but also through the Fermi gas chemical potential. So technically now everything is in terms of n.
Can you remind me what slant for?
Yeah, sorry about that. So lambda bar is the, I think in our case, it's 2 times the renormalization parameter x, which in pQCD is usually varied between, if I'm multiplying by 2, I think it's varied between 0.5 and 2. But in the literature, sometimes they just say 1 and 4 because they ended up changing the way that they scale it. But yeah, so that, and then that is multiplied by the chemical potential. So yeah, so it is directly linked linearly through to the chemical potential. But yes, and that is another thing that I will point out as well on our results is that for this x value that a lot of people in the field vary this or marginalize over this, we chose a single value for now. So that is something that we could do in the future is marginalize over all these things. But you'll see that in a second. Okay. So as far as we know, I think this is the first time anybody's done this in this scheme. Because most of the time what you care about is the chemical potential when you're at this high density regime. But for us, again, because we chose to do our model mixing and density, we care about the number density. So this is what we get if we do this KLW, as we call it, Cohen-Leitinger-Ward inversion. So if you just take a second and look at these mean curves, you'll realize that they flip signs and that now it's approaching from above. But this is purely because of this algebra that's done. So everything is still consistent. I think when I gave a similar talk at UIUC, I think Nicholas Eunice said something like, oh, so it's all in there, but it's at different orders now. I'm like, yeah, that's essentially what you're seeing. So, and I can actually show in a couple of minutes too how we know that this works. But yes, so this is what you get for the means. And then if you want to do some truncation error analysis on this with the same BUQEYE truncation error model, then you need to figure out what your Q and your Y ref are. So in this case, you can choose the Y ref to be this Fermi gas, since that's the first term. And this describes, of course, leading order, as you can see now, as 1 because of the scaling. And then you can also determine an expansion parameter. And for us, we are choosing, which I believe Tyler also chose in his most recent work, is this flavor number of quarks times alpha S over pi. So this is what is producing this kind of behavior here. So this has not historically been done like this. Usually when you look at bands and papers for pQCD, they vary the renormalization scale to obtain the band that they get, which is much, much larger than what we're getting. But they are also currently also working on doing a kind of Bayesian analysis to get something like this as well. What I was going to say as well is that you could imagine that this is much, much smaller than you expect, seeing work that they've done before. But part of that could be because we are fixing the renormalization and not marginalizing over it. So that would be something for future work. So also what we're going to be looking at is that if you pay attention to the scale down here, this is actually plotted from something like saturation to 100 times saturation. But we are only going to care about this range and upwards, because at some point, as you know, you can't use this theory anymore. Even if these truncation error bands look like you could, you know that there are pairing effects and hadronization happening, and maybe we don't know exactly where pairing takes over and is more important than the truncation error that we're seeing. So what we did, instead of just picking a value and sticking with it and saying, oh, we're just going to take 40, we actually look at 2 different cases, which will become important when I show you the model mixing. But just remember that we're taking this range as kind of a prior to figure out what happens to our mixed results depending on where we cut pQCD. So also, in case you're not in agreement on the KLW, we actually look also at the speed of sound, which if you remember your thermodynamics, you will realize that you can solve for the speed of sound like this. But if you're looking at this equation very carefully, it is a number density and chemical potential. And you can take either one and you should get the exact same answer. So what we did was we calculated for P of mu, so the results before, using the Alexandra transformation to get CS squared, but using the pressure. So not in this form, but using the pressure. And then we use this form to get this plot that I'm showing you with the speed of sound from the KLW inversion, and they are exactly equal. and we actually prove this in the appendix of the paper that this is all in. So this was very, very reassuring because it shows that we aren't missing information by rearranging these orders. Okay, so now to the stuff that I have been working on quite a lot in my PhD, as Pablo pointed out. Although I will say that all of that analytical work that we did on pQCD was what took me the longest.
Yeah, probably that was a biased statement of me that I'm excited about the Bayesian part.
Oh, no, totally. No, I totally understand. But yes, I'm happy that we now have a good understanding in our group, I think, of high energy dense matter. Okay, so there are two different ways that we worked through Bayesian model mixing for this. And one of them is this way. And as you will see, this is not the best way. So I do want to get to the very end where I show you the actual good results from the other way. But as some of you may remember, there was an original paper that my group published, and I think this was the work that I gave my summer school talk on last summer, if anybody in here went to that. And this was done with this toy model that I looked at that was an EFT-based toy model. So it's supposed to do something very similar to what I'm showing here. But there are some serious limitations to this, which we figured out as we were working on this project. So what we're going to do is mix random variables pointwise. So model mixing, I know there are people in the room who do posterior-based model mixing and many other different ways, because this is I would still call it an emerging field. But here I'm working purely with calibrated models, so models that I'm not doing parameter estimation for. So we're just taking chiral EFT and pQCD as they are. So no other work going on there. But what we're trying to do is just use the information at N3LO and N2LO of the means and uncertainty bands and preserve this as we model mix. So pointwise means that I literally take every point in these results, which you can already imagine, considering that they do not overlap, is going to be a problem, or at least that they don't overlap in a trustworthy way. But what we decided to do was stick with this and see where this led us for now. So we take every point in whatever density grid that I choose, and because it's pointwise, you have to mix them at every single point. So what that means is I have some variable that is, in this case, the pressure described by chiral EFT and pQCD. I want to find this underlying theory, which we know is QCD, but we're trying to figure out what this looks like in the center, right? So we don't know much about this underneath for the intermediate region, but we do know that whatever this random variable is, it should be this underlying theory plus the uncertainties that we are calculating. And in this case, as I am also going to point out, it's important to remember that these are uncorrelated uncertainties as well. So when you're doing pointwise model mixing, you can only include this, basically if you had a covariance matrix that described all of this, you're just taking these diagonal terms. So you're assuming that all the data points that you're taking from each model is independent, which you can already kind of see is not going to work in the best way because these truncation error bands are highly correlated. But for now, this is what this method is doing. So this is one of the limitations of this method. You can also put, because we're Bayesian, a prior on this underlying theory. So maybe and if you're looking at this and thinking, well, I don't no idea what that would be, then that's basically what we chose for this. So we took this prior to the most uninformative limit that we could. But if you knew something that you really wanted to build in about the underlying theory, that's where you can put it. So then we use Bayes' theorem. I'm not going to show all the math here, but you guys, at least a lot of people know how this works pretty well. And you are basically just estimating a common mean from these two because you know that you're trying to describe the same theory. So you should get a common mean. So this is what the equations end up looking like if you include this prior still. But what we're going to do to make it a little bit more easy to read is to put it in this form where, because I'm doing pointwise mixing, I end up with this precision weighted model where my mean is going to be some weighted mean from each of these curves combined, and then my variance will be some weighted variance. And then if you've seen this before in the other paper as well, you'll remember that that means that each model will take over in its region where it is the most precise, and then when you get away from where it's precise, it will start to the mixed model will start to favor the other model or a combination of the two. So this is what we end up with if we try doing this on the pressure. So there are a few things to explain here. So right here, you have chiral EFT, and this is a little bit darker and it cuts right here because this is as far as we trust the chiral EFT results that we're using. So because these theories don't completely overlap, you can see that pQCD does overlap with chiral, but it's in this region where we absolutely do not trust anything that we're seeing. Then we have to figure out a way to cross between this region. So you can already see that this is going to be biased by that choice because the region that matters for what our mixed model result looks like is the region where we have to figure out what that's going to be to connect chiral EFT over. So this was done, this light pink curve here was done by using an EOS from one of my previous advisors, Prakash, Ainsworth, and Latimer. So if you're familiar with this, you'll also note that this EOS is one of these polytropes that ends up actually going somewhat acausal. So that's something to note that we actually would like to choose. Probably if we were going to do more work on this, would have chosen something that's a little bit more realistic. You could choose APR, you could choose some max speed of sound equation of state or something like this. But the point that I'm trying to make is that you have to make a choice there. So that's going to bias your result if you're using this method. So you can see that this is rapidly increasing because it is following this smaller error band here that is much smaller than pQCD from this equation of state. So, and if you're familiar with how stiff this, what happens when you have a very, very stiff EOS like this, you can imagine that your speed of sound is probably going to be acausal. This is something that you don't want to see here, which is exactly what happens when I look at the speed of sound results. So I get a very, very, very sharp peak here, which is kind of fooling you into thinking that there's a lot more going on here than there probably is, because I know that in a lot of contexts of maybe quark ionic matter, things like this, you would expect to see some peak here and around this region. But this is purely because our EOS is so stiff that when you take the derivative, you end up with this very, very acausal peak. Something good, though, is that it is approaching the asymptotic limit of pQCD from below, which is what has been expected and what we ended up calculating when we looked at the pQCD sound speed. So this is an indication that this method needs a lot of work. So what we did next was ended up trying something that we hoped would include more information. So this was kind of just the journey that we were going down, realizing that, okay, we need to work on what we did previously, because for this kind of case where you have this huge region of unknown, you need something that will be able to cross that, but also use information from both sides in a very principled way that includes all these correlations between points. So in the last method, we threw that out. But if you look at using a correlated approach, we were thinking, okay, so what if we use a random variable like this that has the same underlying theory that we want to get, but now these delta y's are going to be the full covariance matrix of our data, because we have that information from this truncation error model that we developed. So why not use it to its fullest? So this way we're not neglecting any correlations. So also then there's an opportunity here, because as I said before, we can put a prior on the underlying theory. What if we do that, but we use a Gaussian process so that prior looks like a kernel? So this is a way to put in some assumption of what is going on underneath this that we're not quite aware of. So what we did was we chose the RBF kernel, which is very vanilla choice. There are many other things that you can do. We're actually considering using a bunch of other different kernels to build in things. But for a first pass, we decided to use something that enforces smoothness so that we know that we'll smoothly connect these two curves. So this is the same math as before, absolutely. Except for now you have these full covariance matrices going into your uncertainties. And if you do some matrix algebra and you rearrange some stuff, you realize that these equations, when looking at evaluation points, so that's what these E's are, and the T's are training points, you can go open Rasmussen and Williams and realize that these are the GP updating equations. So you can actually obtain Gaussian process equations of exactly how those work with their, or exactly their mean and variance equations from what we were doing with this manipulation from the random variables. So this was really cool. Credit for this ingenious thinking was Jordan Melendez, who came to us and said, hey, remember how you guys mixed the GP into your model? You shouldn't do that. You should just use the GP as the mixed model. So then we went through the math and figured out, yeah, you actually should. So this was really nice because when you build a full covariance matrix in from your GPs as well, you can look at this and realize that your Gaussian process, which I don't know how many of you are familiar with this, but if you train a Gaussian process on a bunch of uncorrelated points, you'll end up with error bars that are much smaller usually than the full error band, because it's assuming, okay, there's redundant information here. If you build it with the entire covariance matrix, you can mostly recover, at least for the Gaussian process, you can completely recover your error bands. So now we're not throwing out as much information either about the physics, because you do not expect to have a more precise model than chiral EFT, at least, unless you've done something much more ingenious than this. So here are our results for this. You will notice that they are a bit smaller, these error bands. So you might be thinking, well, I just told you that that's not the case. But in fact, this happens, but it does not happen because of the Gaussian process. So I'll explain that in a minute. But what I first wanted to point out is that we did this for two different things. So as I discussed before, we don't actually know where pairing comes in exactly in the density, where this is going to take over as the main non-perturbative effect. So we decided to train pQCD down far to about 20 times saturation. And then we decided to be more conservative and only train from 40 and upwards. So this actually affects the results quite a lot. So it's kind of an ongoing study for us as well to see how these different priors change our results. So this is with 20, and you can see this is a little bit stiffer than what you end up with at 40. And if you look very closely, the training points I'm using, there's only like, I think 8 on this plot, and I think 9 that I'm using here. So you don't have to include too much information, and you'll still recover most of the physics that you care about in these regimes. But you'll also see that how far down you train with some of these models actually makes a big difference. So here, we actually also pass through the heavy ion collision data that I'm plotting in this dashed outline from Pavel from 2002. But we're kind of missing one of the theories that's in the center that I didn't really talk about here, but there are some intermediate theories that have been solved. This is FRG, so functional renormalization group, but their error bands are obtained from varying a parameter. I think it's varying their cutoff. So what they do isn't actually well quantified in the Bayesian sense. So we're not including it in the mixing. But you could see that, like, if you really wanted to, and you had a good theory in the center that had well quantified uncertainties, you could mix it, and you might actually be able to better constrain this region. So if they improve their error bands at some point in the future, it would be very nice to see that, to see what we would get if you included this. So something I did want to point out as well is that because we're using an RBF kernel, they're infinitely differentiable. So by just using that and not doing anything more interesting, I guess I would say, you're suppressing the idea that there's some kind of discontinuous phase transition here. But you can imagine that you would be able to build this in some way. And I know that some of my friends at UIUC have been working on figuring out how this might look. And also, the fact that we're using a GP here as well means that usually if you use something like the RBF, it'll be a stationary kernel. It assumes that your data looks pretty much the same across the whole region. But for us, we know that that's not really true. So maybe in this log scale, it kind of looks similar. But if you take it out of the log scale, you'll see that chiral EFT is much more rapidly increasing than pQCD, right? Because pQCD varies logarithmically. So we trained in the log scale to kind of get around this. So our kernel is a little bit non-stationary in that sense, but you can imagine that it might be useful to build one that is completely non-stationary so that you can build in more effects. But what I really wanted to say as well is that if you are confused about why chiral EFT's error bands are still bigger than what we get, this is actually just a product of doing exactly what we were doing for our model mixing. So we're combining random variables. And if you look in a lot of the statistics papers that we've looked at, it's a well-known fact that if you're combining Gaussians in this way, you're going to end up with either very, very close to the same size or smaller uncertainty bands, if you're assuming what we have assumed. So this is not something that is implying, this figure does not imply that we know more about chiral than we're saying. This actually is just implying that this is an assumption of the method that we're using. Okay, and then the results on the speed of sound side. This is the kind of the same analysis that I just went through. So you'll see that there's a peak around here. I think this is about 8 or so times saturation. Again, this is an effect of differentiating the Gaussian process. So there's not a lot of, I would say, tinkering under the hood going on here or anything that we're not showing. It's just something that happens as you look at these models. So this very, very smooth pressure curve is going to end up with a very, very smooth speed of sound. But it is interesting to note that depending on how far down you train, this peak gets much more pronounced. So it could be like a further study to see exactly how sensitive this is. And if you trust pQCD down that far, and there's actually, if there's more coming out about this, then maybe you should trust that further, then you know that you can train down farther and this effect will be seen. Yeah. But it is very, very reassuring that we end up with a stable causal EOS when we try to use it, at least this formulation of the Gaussian process. Okay. So this is what essentially is in the paper that we put out about a week ago on the arXiv. So if you want to go look at that and ask me questions about it afterwards, go ahead and do that. So this is the study that we did on symmetric nuclear matter, like I just explained. And there are new results in the sense of this P of N calculation that we did for KLW inversion, this truncation error from BUQEYE being applied for the first time to pQCD, and actually trying to kind of solve this very difficult problem of connecting across densities that are absolutely unrelated in terms of scales. So this has been very interesting to look at. And what we would like to do next is to look at applying this to something where I have more information that I can compare to or that I can use in the actual model mixing. So that would be in the asymmetric matter regime for us, where we could actually include astrophysical observations. We could look at mass radius curves and nicer data and see how the variations in this model mixing, or what we get from this GP, how that affects what is being observed, or how what affects what is being observed affects what we should be doing with this kernel or with this Gaussian process model. And also, of course, there will be data from FRIB 400, and there will be, and there are also other constraints that people like this paper from Sabrina have used that we could also include in what we're looking at. But of course, the goal would be something where we would have a completely QCD-based equation of state on the model side. That would be very useful for neutron star mergers and simulations. But obviously, we're not quite there yet, but this would be what I will be hopefully working on in the next few months. And with that, I would like to thank all of the people involved on this project, my PhD advisor, Daniel Phillips, especially my collaborator, Christian Drishler, who put me on the FRIB seminar list 2 years ago from my first model mixing paper. So I'm glad that I actually have an interesting physics application to show for this, and all of the other people involved, also Ascension. So, gotta give credit. So thank you.
Very well. Thank you so much, Alexandra. Fantastic talk. I enjoyed it a lot. And I'm going to go with questions. Patrick.
Hi. Yeah, but this is the longer than 7 minutes final version of the one. Yeah.
I mean, you said that.
Mhm.
You go back to the 12 part about
Here.
yeah, so I was having trouble hearing exactly if you said it's suppressing the discontinuous basement or continuous.
So it's, I mean, in a sense, it's suppressing I guess both of them, because when you look at the GP, it's like there's no way to, at least in our kernel, there's no way to really build anything in, because it's this infinitely differentiable guy. But
I don't think we expected discontinuous, not a virtual.
yeah, so I mean, there's some expectations that you could build that into the speed of sound and end up and go backwards to the pressure. And then that might be a discontinuous phase transition in the speed of sound. At least that's what I've seen some people do. I'm not sure if that's absolutely expected anymore. But in the number density, you expect some kind of phase transition there.
There's no path forward in all
No, I think you could do it. One of the reasons why we didn't really do that in this paper, other than timing, was that we wanted to do something that was as model independent as possible. So because you don't really have a way to validate whatever you're going to build in, that would be, again, model dependent. But like I was kind of hinting at during the talk, like Deborah at UIUC and her advisor, and I think Veronica Deckheimer, have worked on building these into the speed of sound. So they have like built a modified Gaussian process model where they're able to build in what they call, kinks in the speed of sound, and then, or maybe even in the pressure, and look at what that does. So you can do it. And I think that's an interesting path, but I'm not sure if that's where we're going to go immediately. But yeah, I think it's doable. I think it just depends on how you want to do it.
Thank you. I'm waiting this way and then I'm going to Daniel.
First of all, nice talk.
Thanks.
How did you decide on how many training points to have? And did you consider varying the location of them?
Yeah, so we did that. Yes, good question. We did that especially with the pQCD one, because, and I think also with Chiral. So as long as this one is obviously the one that varies more. So when we were looking at this, it is important that we pick points in a certain range, I would say, for Chiral. We didn't pick all the way up to where the data is, but that didn't really matter so much as where we picked out here. So it did matter that we had something below saturation, at least when I was playing with where we should put the training points. But when we looked at how many we used, it actually didn't matter, which I think is a product of putting the full covariance matrix in, which is great because I did try something like using, this overkill and like using all pQCD, and it was the same result. So I think that doesn't vary. But I would say like with ones like this, which I also noticed when I did my toy model paper that have a lot of variance, it is important to at least put points like the anchors on both sides of that model. Yeah.
I'm going to complement Daniel's questions. Given that this is a band paper, is there any way that us mortals could play with your results and change things and try to create new equations?
We're gonna release this because we are, well, I mean, band and BUQEYE are like, open source code must occur, which I totally agree with. We're not going to probably release this until the paper is accepted, but we are going to release this. So you will be able to play with this probably in a few months, I would say. Yeah.
Scott.
Yeah, very nice talk.
Thanks.
So how would you expand this if you wanted to account for the many body truncation errors, as well as things like variation in the QCD normalization scale, the Chiral EFT?
So I think, so for things like the renormalization scale, I think we could, in the model itself, marginalize over that if we wanted to, because there are quite a few things that I would say a lot of what's kind of nice about this is that if you want to do very specific things with the models, that's on the model side. So you don't really have to build all of it into the model mixing part. For the regulators or for the many body calculations, I think it would be, again, something like that. At least with the many body one, I would think that you would build that outside of the model mixing so that that truncation error or whatever that error is that you're picking to go into the model mixing itself would include that, if that makes sense. So it would be something done externally from the actual Gaussian process modeling and such.
does that assume that the EFT truncation errors and the many-body errors are?
So this includes it because this is at least the chiral EFT one is the one directly used from the 2020 paper from Jordan and Christian, where they, I think, choose, so they quantify the truncation error. But then they also include, I think, a white noise kernel to account for the MBPT errors, because their errors were so much smaller than the truncation error that was good enough. But I think if you wanted to play with that more, I think it would be something that I would consider doing before you look at the model mixing, and then you would use that, yes. But yeah, there are these different regimes of where things would change, and I think that's a model question and not so much a model mixing question, yeah.
Betty,
Yeah, I was just surprised at how narrow. it's like, how do this be-
Yes, so,
especially compared to-
oh yeah, absolutely. So I was expecting to get this question. So we also do not think like, oh yes, this is so well constrained. We know exactly where this is. So part of this is the at least part of it in what I've seen from using RVF is that sometimes they're a bit narrower than I would expect. But also a lot of this is coming from, as you can see, it connects very, very well to pQCD. So the fact that our pQCD truncation errors are so small is what is actually driving this to be very, very small, because this length scale is quite long. So it's remembering that these pQCD errors are small and kind of propagating that down. So there is the question, as I was saying, with the renormalization scale, if I marginalized over that and it made these bands bigger, I would assume it to be larger. So there are a lot of, because of that assumption that these pQCD error bands are small, I think that is what is driving most of what you're seeing in the center. So it depends a lot on the error bands from pQCD. So that is something that we want to look at if we continue this.
maybe in the same way as you were not 100% sure to even trust pQCD with some error bars, that's why you quantify, you said, let me try to see what happens if I trust it up to here.
Yeah.
There is a way to include more error budget in that final band that doesn't come from the smooth structure of your points.
Right.
We have time for one more question, Pablo?
This is a small one, so, my memory, chiral affected theory has a problem with producing saturation font. So what will you do at that end? Do you add extra error compared to what at least one released the data?
So far, we haven't done anything different with chiral in the saturation point. We're picking the 0.164 that Achim and Kai, I think, developed quite a few years ago. But I know there is work being done on that.
I guess.
So yeah, so if there is a way, or if there are better results for this to include, then I would say as soon as that comes out, we can use that. But so far, yeah.
Do you stick religiously with affected theory, or do you add extra? Answer.
So for this one, we just stuck with chiral down to 0.05, yeah.
Very well, let's all thank Alexandra. I remind the grad students that we're going to go for lunch with her, but after that we have dessert and coffee between 1 and 1:30. And from everyone, you can still schedule meeting time with her. She's going to be here for a couple of moments. Thank you, friends. I don't know, we have to step there for it.